Earlier, we had talked about the importance of the activation energy as well as the orientation factor. Now, it turns out that when the collision happens between reactant particles, they don't immediately become products. They actually form a species in between reactants and products that has a very high energy. And this is what we refer to as the transition state molecule. So here's an example. You have a reaction between N2O and NO to form N2 and the NO2 molecule. So the transition state, or the activated complex, is the molecule where the bonds that need to be broken exist and the bonds that need to be formed also exist. So it's far from ideal for the molecule, right? Because you can't have that many bonds. Many times that would violate the octet rule for certain molecules. So its existence is not going to be tolerated for too long. The molecule will have to switch, either going back to reactant or converting to product. The transition state complex is reversible, meaning that you can switch back to reactant or you can go to product. So it doesn't have to just go one way. And the way we illustrate this process from reactant going to transition state and then going to product is using something called the energy diagram or the reaction profile. First, you start with the two axes here, where the y-axis here represents energy or enthalpy, and then the x-axis represents something we call reaction progress or reaction coordinate. And basically, what the x-axis represent is on the left side, you start with reactant, on the right side, you end up as product. The goal here is to illustrate the energetic stability of reactants, products, and transition state. If your reactants has energy drawn right here and your products have energy drawn here, so that tells you that the product is more stable than the reactant because it has lower energies. And then remember that the collisions must happen between the reactant particles to generate the transition state. So the transition state must be a higher energy species than both the reactants and products. So it exists somewhere here in the middle. The energy diagram itself is just a connection of these three states right there. In addition to that, you see some numbers. So I want to point out what the meaning of those numbers are. So the first number you see is 209 kilojoules and it says EA forward. So that number actually represents your activation energy. So the reactants must collide with a minimum of 209 kilojoules before your reactants can form the transition state. We call that the forward activation energy because it represents how the reactants is going to transition state. And it's just the difference between the height of this level in the energy with the height of the transition state. Remember that transition state is reversible. If you can have the forward activation energy, you can now also have the reverse activation energy because the products are constantly moving as well. They all have some kinetic energy. It's possible that the products are going to collide with other product molecules and they can reform the transition state. So we can now calculate something called the reverse activation energy, which is just a difference between the energy of the product and the transition state. And as you can see, this number is bigger, 348 kilojoules. So clearly in this case, it's easier for the reactants to get to the transition state because there's less of a barrier to get there, less of an energetic barrier. And then the last component of the energy diagram that we need to highlight is the difference between the energy of the product and the energy of the reactant. So this level with that level right there. And that actually is your change in enthalpy. So you might remember that from Chem 11, when we talk about thermochemistry, we measure these change in enthalpy using calorimetry. Now, in an energy diagram, we can also incorporate that number. Delta H is just the difference between the forward EA and the reverse EA. If you want to calculate it, all you need to do is take the forward EA minus the reverse EA. If you do it for the reaction that we were just looking at, you get negative 139. And of course, what that means is it's a exothermic reaction. So here's an example of an energy diagram where there's an endothermic component to it. You can see here that the forward EA is a bigger number than the reverse EA. And in this case, if you subtract the forward EA, which is this quantity right here, minus the reverse EA, which is this one right here, you get a positive number. And so your delta H here is endothermic. Okay, so now we want to apply that concept about the energy diagram that we just learned to this example. It tells us that there's two reactions. One reaction is between G2 and E2 to form 2EG, and that's that's the exothermic reaction. The other one is G2 with X2, and that forms Xg, which is endothermic. The first question here just says to sketch the energy diagram for these two reactions. They want it on the same graph, but I'm going to just split it to make it a little easier to see. And so this is what the plots look like. On the left side is the exothermic reaction. The way you want to do it is you start with the reactants and products, making sure that the products is lower in energy than the reactant, the product's more stable. Then at the transition state, which is going to be in the middle between the two and higher in energy. And then you want to label your axis correctly with enthalpy on the y-axis. Sometimes you'll see energy as well, and then the reaction coordinate on the x-axis. For the endothermic reaction, you just need to flip the relative position of the reactants and products to make the product now less stable than the reactant, and then you'll have the same components for all the other parts. I think one of the questions that sometimes people ask is, why would an endothermic reaction even take place if the product is less stable than the reactant? And the reason is there's some other component that determines the stability of products, and stability of the bonds is definitely one component, and that's what's being measured by enthalpy, but there's also a second component called entropy that we would learn later on that also determines how stable products are relative to reactant, and that's why in certain cases endothermic reaction will take place. The second part of this question has to do with calculating the reverse activation energy. So it says if the exothermic reaction has an activation energy of 125 kilojoules and then the enthalpy is negative 40, what's the reverse activation energy? So what you need to remember, of course, is that the enthalpy change is just the forward minus the reverse. In this case, we were given the forward. It didn't say forward specifically, but the question did ask for reverse, so we know that the number that we're given is forward. You can set up that equation, which I did here on the right side, and just figure out that delta H is forward minus reverse. If we're solving for the reverse, then it will just be equal to the forward activation energy minus delta H, and then we plug in the numbers, keeping in mind that the delta H itself is negative 40. That gives us 165 kilojoules as the reverse activation energy.